geothermal and how we can really connect subsurface to surface, and what type of advancement on the new approach for accessing to the geothermal reservoirs through stimulation techniques. So I am a global lead for geothermal and unconventional from Reservoir Technical Services within Baker Hughes. And I would like to start with what type of risk that impact ultimately on the success of the geothermal project. So if you look at the risk category, we can look at it from three different aspects. From project feasibility and the risk associated with the subsurface. So do we understand the reservoir resource risk? What type of engineering and design approach we need to bring based on the reservoir capacity and the reservoir characteristics, and also operate compliantly. The second category is execution risk. So how we can plan and execute perfectly, what type of project management and the qualification we need to put in place. And on the execution, it's not only on the subsurface piece, it's also the surface portion. So choosing the right technology on the well construction, completion, and production space, as well as generating power and bring efficiency higher by understanding the reservoir characteristics to link to the surface technology. The third category is economic risk. So as you know, the upfront cost of the geothermal development is very high because of the high risk. So how we can spend our money wisely during this development cycle. And the other component, which is very critical, is time to value, how we can reduce the time to reach to first megawatt. And it requires the multidisciplinary approach, that how we find the resource, where the high temperature, high viable reservoir is, and how we can select the right surface equipment in terms of power plant, or even when we are talking about district heating. So what type of service facility we need to provide, and how the design cycle needs to be defined in terms of time and material and the risk in order to reach to first megawatt faster. And when we can prove that the resource is viable, then we can secure financing for the development of the project in geothermal space. So in order to take energy forward, geothermal energy forward, I can emphasize again on integration between the subsurface and surface. So what does that mean? It means that we start with the front end and engineering and feasibility and come up with field economics before we start to go through appraisal or exploration drilling. So we gain more knowledge on the subsurface in terms of the rock, fluid, geology, petrophysics, geomechanics, all the components that really define the subsurface characteristics. And then we start to provide the well construction solution and design. We drill a few wells, exploration wells, to confirm the resource is viable. And we validate the thermal production or power output of the resource based on the exploration and appraisal wells, and then you design your field development and then surface facility. So there are different components that needs to be integrated both on the subsurface and surface side in order to reach to the power generation. Today, we are looking at it from the technology perspective, from the financial perspective, different commercial models, and digital. So how we can better monetize our strategy with different type of monitoring, pre-drilling all the way to the production period. So if you look at the project development cycle, it starts with resource assessment and resource development, and then power plant construction, and then operation. So usually the first two sections takes between 7 to 8 years in order to reach to define your number of wells, drilling the wells, and having a set of wells injection production to access the reservoir and start to produce the hot brine. And then you start to commissioning and operation, which can be a long term, 25 to 30 years. So this is the series of steps that we traditionally took. So what we are looking at today, in order to really understand the risk and assess the risk and mitigate the risk and bring more economical advantages to this project to be successful, instead of series of the events, we would like to have some parallel steps. So how we can coordinate a multidisciplinary team in order that the reservoir engineer, geoscientists, to talk to the engineers on the well construction as well as the surface piece, right? So by that integration and communication and collaboration, you can really shrink the timeline so you can start your power generation much faster. And that goes back to reach to first megawatt in the shorter time, which means that you will reach to your cash flow much faster. So this is one of the approach we are taking. And as a Baker Hughes, as a technology company, that we are one of the few that we have all these components to put it together in order to make the geothermal projects much more successful by understanding the risk, mitigating the risk, and bring the right technology for the development. So I want to a little bit deep dive on the subsurface to surface concept, and what does that mean in terms of investment from design to commercial success of these projects. So if you look at the geothermal system, we are looking at it from the conventional system versus unconventional system. So conventional system, which include the heat pumps, which is more shallow resources and for cooling and heating of the buildings units. When we are talking about more hydrothermal resource, that we have heat, we have fluid, we have right permeability and conductivity in the rock. So like what we see today in Iceland. So that means that we are still in the unconventional system. When we go a little bit deeper and in a volcanic system rock or either sedimentary system rock, and we don't have enough permeability or fluid, which are the most important component for the geothermal power production, is that how we can design the engineered system. That's how the enhanced geothermal system, or EGS, or in another concept which we call it closed loop versus open loop, requires different type of approach in terms of reservoir creation and stimulation with higher pressure fluid or creating more permeability through injection cycle between injection and production is one of the approach that today we take. So why it's important to understand the reservoir characteristics in terms of rock, fluid, and brine composition? Because based on the resource condition, we need to select the surface technologies. So it's very temperature dependent, and the type of fluid or brine that we see at the wellhead. So you can see that we can categorize it between steam dominated, water or steam mixture, or water dominated. So when we are looking at the low enthalpy, we're still in the water dominated, and we need to use different type of surface facility or technology to generate electricity, which we call it binary system, or ORC, or organic Rankine cycle. That it requires a lower temperature fluid from the reservoir, and we need to bring secondary fluid for power generation. When you look at the high enthalpy system, we can look at different technology for the surface, either dry steam, single flash, double or triple flash. Again, it's all about what we see in terms of fluid phase at the surface. So various stage for geothermal development can be defined in finding the site that we are understanding what is going on the subsurface side, right? So we provide feasibility analysis from some geophysical surveys at the surface before we drill the well, or if the well already drilled, we can use the offset well data. And then field to field is different, formation to formation is different. Then we start to design our exploration strategy. We drill a vertical or directional well. We do the flow testing. We fine tune our subsurface models and understanding. We fine tune our well design when we are going to field development plan, that we start to drill more wells, and that's in that section, the drilling optimization, completion optimization, in the case that we need to have a stimulation design. So we start to fine tune our strategy during the development based on the knowledge we get from pre-exploration and exploration phase. In the more mature field, that like Indonesia or Turkey, that the wells are producing for years, we can see that there are some challenges around the thermal decline because of the pressure depletion, cooling effect near the wellbore, the reservoir characteristics changing with time. And as you know, the brine and the fluid rock interaction in geothermal could be very challenging. So the production challenges is around scale, corrosion, and that these are some of the solutions that we need to provide in order to improve the production when we see that the heat production starts to decline. So economics play a key role for geothermal. So if we cannot economically prove the viability of the geothermal development, the project will stop. And sometimes we see that the geothermal project bankrupt because we don't go through the steps that we need to take. First, we need to understand what type of resource we have. So resource evaluation and classification is critical. By knowing the heat in place, what is the technically recoverable for the reservoir, understanding the risk associated with drilling, completing, and production based on the rock and fluid composition and the temperature component. And then also we need to look at from the techno-economical evaluation. So what type of investment, what type of capex we have, what type of opex we have, what is the heat selling price, project lifetime, and some maintenance issues, and ultimately what is our key component at the wellhead, which is flow rate, pressure, fluid composition, and temperature. So these factors really dictate that how much power output you have. So based on that, we look at it from three categories: capacity, injectivity, and integrity. So what does that mean? So capacity means that how much we understand the geological setting. So in terms of fracture system, in terms of porosity, permeability, rock matrix, rock mechanical properties, thermal properties, petrophysical properties. So this is the first step we need to take. And then the next is injectivity. So focus on that, how much reservoir can deliver by approaching different technology and implementation of the design in terms of well construction or in terms of completion or completing the intervals or stimulating the rock in order to have access not only near the wellbore but far field in the reservoir. And the other component is integrity. So why it's important? Because you can see that the rock is hot, the fluid is cold, so this temperature contrast is bring more challenge. The geochemistry of the brine with the rock mineralogy could bring different challenge. So wellbore integrity and cement integrity and caprock integrity, these are the really key components. And you can see, for example, about 8 months ago, there was a project in France had to be shut down because they really reactivated the fault and fractures, and they induced seismicity. So environmental aspect is very important in order to have a safe operation, and ultimately the whole integrity aspect needs to be considered. So I would like to highlight what approach we take as holistically and showing the workflow that we are using for geothermal projects from beginning to end. So usually project to project is different. So the type of data acquired in the field is different. We can start with more field scale data like 2D, 3D seismic or geophysical surveys like MT magnocaloric and other stuff that they acquire at the surface, or some sampling from the fluid. If the well already been drilled or there is some well log data is available. So these are the different type of data at different scale. Sometimes we have a core information or cuttings from the drilling that we can really look at all the mineralogy of the and geomechanical properties of the rock. So how we can integrate all this information on one platform and then build our structural framework and then map the properties based on the information that we have from the field and well, and then build our geomechanical and petrophysical and geological model. So, and I want to a little bit go into details on the geomechanics and the fracture system, because this is a key component for geothermal development. We highlighted induced seismicity and the macro earthquakes, so how we can monitor this system, how we can make decision and couple that with geomechanics in order to have a safe operation, and ultimately how we can predict the power output based on what we have from the field. So heat flow dynamic piece, which is playing the key role on the reservoir simulation side in order to link all this information to predict what will happen. So as I mentioned, most of the project starts with prospecting in order to gathering different geophysical surveys at surface. Electrical methods, thermal methods, or indirect methods that we show it here, like TEM or MT, some of the direct temperature and heat measurements, or magnetic survey, gravity surveys, or the seismic surveys. So based on this information, we can build our conceptual model. We also can go a little bit deeper based on the data availability to use seismic data and use inversion method and using different seismic attributes to map the heterogeneity of the reservoir, to understand the structure, faults and fractures from the seismic information. Integration of the well data with the seismic is another step if the data is available, so we can understand the heat capacity, geothermal gradient, thermal conductivity, geomechanical properties like stress and rock mechanical properties, as well as some of geochemistry and biochemistry of the field. And then all of this information could be integrated in order to better understand the reservoir, improve the efficiency, reduce the cost and risk, and ultimately maximize power output. So today, we have access to advanced modeling techniques, softwares, computational horsepower that we really can digitally experiment all of this information at a computer instead of try an error in the field, which is very costly. So why geomechanics is important? So understanding the rock mechanical properties, stress state, stress magnitude, fracture system in terms of orientation, intensity, size is critical. So there are different ways that we can measure these parameters, or we can interpret these parameters and then integrate it in the subsurface or geomodel to understand that how our reservoir boundaries are, what type of secondary and primary path for the permeability, either it's rock matrix porosity or permeability, or it's fracture driven. And for example, we see in some part of Indonesia, most of the rock has a low, like zero porosity permeability, and the main factor for the flow and heat transfer is fractures. So how we can better understand the fracture system and map it into our models. And it's beyond the static model. So we mentioned about the complexity of the geothermal system. It's a coupled system. Thermal, hydrological, mechanical, and chemical components are coupled. So, and each of the components can impact either short term or long term during the production cycle. So we start with the 1D model around the well. We build our static structural model and geological model. We run the reservoir fluid simulation, and then we are looking at pressure and temperature changes in time. So that's why we call it 4D. So it's beyond 3D, it's 4D because time can change the properties of the reservoir. It can impact on the heat transfer and ultimately what we can see at the wellhead. So on the stimulation strategy, which is more towards the EGS system or enhanced geothermal system, we need to create permeability within the reservoir because we don't have enough flow path for the heat and fluid to transfer from injection to production well. So one of the terms that we are using is hydroshearing. So what does that mean? It means that we know that the fracture exists in the rock. So we are going to increase the pressure by injecting the fluid, and we open this fracture, and this fracture can slip and shear, and you can improve the permeability. So opening the fractures during a stimulation or hydroshearing, or we call it self-propping, is one method. And usually, in this case, when you look at the unconventional or horizontal drilling and multi-stage fracturing, what we see in the shale from shale gas and shale oil is that you increase the pressure above your frac gradient. In this case, in the hydroshearing, we are not creating the new fracture. The new fracture might create during the thermal cracking and the interaction of the cold fluid and the hot rock, but basically we are opening the pre-existing fractures. And we measure the permeability based on the different approach and models that we have today. And I'm showing here one of the fields that we modeled in Indonesia, that how the fracture permeability look like after injection and production. So hotter color shows that we have higher permeability in the system. So this is one way to really look at how you want to do your well design. So you want to put your wells, you want to design your wells in order to intersect this fracture, and these fractures, if they are critically stressed during the injection, they get open, and you can create a better flow path for the hot fluid and the thermal transfer to the production well. The other approach that we see today for example, Force project is doing, or some other EGS project in North America, is to use high pressure stimulation, where when we are creating the new fracture, the way that we are creating the fracture in unconventionals. So I'm showing here one of the cases that this is the wellbore. We have the multi-stage hydraulic fracture. So we increase the pressure above the frac gradient. So you break the rock, you create the fractures, and then your main fractures could intersect your natural fractures. So you will have the mix effect. So creating the new fracture, new aperture, new surface area, as well as opening of the pre-existing fracture or natural fracture. So this is some of the new approach that we're taking to adopt what we learned from unconventionals to bring in geothermal using proppant. It depends on the temperature. It depends on the rock system, obviously. But the existing technology could be adapted to some of the geothermal setting and system if the temperature allows us. So in summary, I would like to highlight the importance of the integrated subsurface model. Understanding the temperature. So you can see from this model that it's not layer cake. So your temperature gradient is changing from one section of the field to another. Reservoir pressure is important to capture. So there are different technologies to measure temperature, pressure, and better map the characteristics of the reservoir. Rock mechanical properties in terms of Young modulus, Poisson ratio, and other factors that how we can better map the rock properties that ultimately impact on our engineering design, how we can drill the wells flawlessly. So when you look at the geothermal drilling period or duration, it's between, in some of the challenging cases, it can take from 40 to 80 days. Today, in North America, in the unconventional reservoirs like Marcellus shales, we can drill the well, horizontal well, multi-thousand feet in 5 to 7 days. So comparing the drilling duration, because the rock is different, because the rock hardness is different, so how we can better map the properties in order to understand the risk on our technology we want to deploy in order to reduce the drilling duration, during drilling risk, and other components in order to make it faster and more efficient. And then what impacts directly on our production is understanding our fracture system, especially for the EGS or enhanced geothermal system, because these primary fractures are the main path for the heat transfer and production level. So when we are confident about our subsurface model and we do our validation and we integrate the data, so we need to transfer the subsurface model to the reservoir simulation. So it requires different approach, different steps, because usually we have a different scale model from the geo model to the reservoir model because of the numerical grid size and the numerical iteration that we need to have. So we are developing different approach in order to bring the fracture system and the permeability model to the reservoir block, which is ultimately can dictate us how we can fine-tune our field development strategy. And the reservoir simulation or heat flow dynamic is really tell us that from the wellbore to reservoir, how much heat we can produce, what is the enthalpy level, what is the megawatt we can produce based on the model input. So when we build our model and we run our reservoir simulation and we have a base model, we can start to design our sensitivity analysis, which is very important. And this is go back to my point that let's experiment digitally instead of try and error in the field. So there is a lot of uncertainties in the parameters that we take in our models. So how we can look at it differently if we run different scenarios based on the uncertainty we have on the data side, on the temperature, fluid properties, rock properties, phase transition between supercritical or vapor, so in the more higher and deeper section of the reservoir, fracture system. No, we can all the discrete fracture systems, it's not unique. So how we can better map the subsurface structure for our modeling purposes. Heat capacity and thermal conductivity. And then we can start to play with the design. So how many injection, how many production, what is the injection and production spacing, how should the well trajectory look like based on all we get from the subsurface model. And in the case that we require a stimulation strategy, okay, how many stimulation zones we need? Do we need to stimulate only on injection or both on injection and production? How many zones? What is the interval size? What type of flow rate? What type of fluid type? Or do we need proppant in the case that the proppant can survive at that temperature? what is the temperature of the injection fluid. So all these components can be modeled today. And we are testing these scenarios to come up with thermal output calculation. And this is one of the examples I'm showing, that how many models we can run in order to see that what type of engineering recommendation we can bring in the picture to bring the production from the base case to the higher level. And ultimately, we would like to understand the enthalpy and the energy output in terms of megawatts. So I'm emphasizing on the modeling side because we can get a lot of knowledge and make a decision based on the models to see which way is better to investigate in the field and operation and deployment of the technology. But it's not going to stop here. So when we have our heat flow dynamics, so these are the 3 steps that I was explaining to you: the subsurface model, well design and completion design, and a stimulation design, all the way to the heat flow dynamic to understand the power output versus time, wellhead temperature, pressure, rate, and fluid or steam quality. So what is next? So the subsurface to surface piece is this part. So when we have this information from our model, how we can better communicate with the surface people in order to understand what type of the power plant we want to design in terms of size, in terms of material selection, the efficiencies, the plant design specification. We have other components at the surface like condenser, cooling tower. So this all can come together if we can work all together at the same time by understanding the subsurface characteristics. These are some examples and projects that we delivered globally in different regions, Asia Pac, like Australia, Indonesia, some pre-feasibility in Africa, also in North America. So again, this workflow has been deployed more or less based on the availability of the data and the outcome that we want to achieve for our customers. But this is how we want to make sure that the geothermal projects moving faster by bringing better modeling techniques and better understanding of the subsurface before we start to design our fields. So that was my last slide. So I think I would like to open the conversation for questions.
Okay.
Cesar, back to you.
Thank you so much. Okay, thank you so much. And that is a very interesting presentation. So I'm going to go through the questions. Okay, I'm going to start with some with the audience. One is how to manage the durability of thermal stimulation as time passes and that area heats back up. Also, in addition, cold fluid causing contraction of rock material, but how sustainable is that in terms of flow, elastic or plastic deformation?
So yeah, that's a very good question. So the thermal simulation, or the 4D concept that I mentioned, that we look at that how the properties of the fluid or the rock changing by time, right? And today we have ability to use physics-based models to predict that how this characteristic will change, right? How our pore pressure is changing, how the cooling effect near the wellbore, far field. However, this information needs to be verified. So that's why we are providing different type of sensor and measurements to monitor the reservoir changes during the production. And based on that, we are fine-tuning our models. So the thermal models today is based on the physics, but it needs calibration, right? And that's why the monitoring technology is required in order to manage a reservoir long term.
Okay, thank you. Okay, second question. In your experience, how efficient are the open hole completions for stimulation? The issues with flow control? How high pressure, high temperature sleeve completions be better in terms of isolation and stimulation intensity?
Fantastic question, because most of the geothermal wells are open hole, right? And the zonal isolation is a key component for successful stimulation. And when the temperature is going up, sometimes these tools are not survive, and we might have a short circulation, and we might not have the effective stimulation. So we are developing new technologies for zonal isolation for higher temperature. Also, you can see in the new EGS development, like what we see in Forge, Fairbow, some of the projects that is carrying in Canada, Deep Energy, they are using case and perforation, exactly what we are using for unconventionals. So the question is that when we are using the unconventional approach, can we design the right hole size, right, and perforation strategy in order to get the right flow at the wellhead? So you can see that the well design for the geothermal is different, because as much as flow we can get from the subsurface, right, based on the flow rate that we get and the temperature and pressure, that directly connects to your power output. So I think there is a lot of advancement will happen on the stimulation in terms of new packers, right, for zonal isolation, case perforation for this new EGS. When we have the like a sedimentary rock, there is a horizontal drilling is happening for EGS, which we never had it before, right? Most of the EGS projects were vertical or directional. So more projects like Forge and other projects that's happening in Nevada or Canada, they will bring a lot of experience for us that how we need to move forward for EGS development.
Okay, thank you. So now that you mentioned this, okay, horizontal drilling, what are the advantages, considering that horizontal drilling is also more expensive, but if we not like comparing exactly what happened in oil and gas, but what is specifically the advantages of drilling horizontal wells in EGS or in geothermal developments?
So I think on the sedimentary rock, when we don't have the very high temperature, because directional drilling and advancement for unconventional is a key success for unconventional development, right? Mm-hmm. So how we can better navigate our drilling in the formation and in the pay zone, right? How we can create the larger surface area. So if we can identify our surface area in the higher temperature and create more fracture stages along the horizontal, if we can drill at that temperature, so you can create more flow path between injection and production well, right? So I think that is the key, that, okay, how we can bring the higher temperature back to the surface, right? With more surface area we create between injection and production well.
Okay, this is like, gestating, but looking into hot spots, To the
hottest spot, to intersect the fractures, right? Because ultimately, when you inject the fluid, you want to create the fractures open, right? You make the fractures open. And so geosteering is critical in order to intersect the right fracture system in order to improve the permeability ultimately. Okay,
thank you so much. Okay, another question, a lot of questions actually. After developing a hydraulic fracturing, how will it be possible to manage and avoid channeling generated by the artificial fractures? Because geothermal reservoirs needs to show an uniform flow to warm the water injected.
So yeah, lost circulation is one of the key challenges, right? Because if we have a path like a flow path or high permeability channel, which is not communicating with your production well, so you are losing that fluid into the reservoir, right? And you are not capturing that. So that's why the understanding the structure and the system is critical. And then in the cases that we see that some of these challenges is coming, so how we can design your future wells to intersect those or to infill drilling basically in order to improve the communication of the fluid flow from one well to another well when there is not much communication between the original design. So infill drilling, better resource assessment and understanding the structural part of the reservoir is critical for this problem.
Okay, thank you. Okay, I have another question. I'm gonna read this one. Okay, let me check. Okay, what is a typical distance between injector and producer in EGS stimulation based on experience? And additionally, based on your experience, what would be a safe distance from faults B when doing injection? Okay, this is to avoid seismicity. Okay, that's it.
Okay, there is no single value for well spacing, right? So we see that some of the demonstration EGS project they have 200 to 500 to 600 meter well spacing, right? Again, it depends on that. What is our okay? So I go back to oil and gas concept because first it's about your asset. So how much resource you have, right? What is your resource boundary? And the second is about your surface facility. So how much surface constraint you have. And the second, and first about the subsurface, that what do we know and how we want to design our well in terms of injection and production and how link it to the surface constraint. But so it depends. I see different well spacing in different EGS projects. So are they successful or not? It requires more investigation to see that do we need infill wells, right? Because we don't have enough communication, right? We don't see enough rate. We don't have enough temperature or pressure at the wellhead. Mm-hmm. In terms of fault reactivation, so it's all about understanding the stress state, right? So which stress regime we are in, and when we are injecting fluid and increasing the pore pressure, how the fracture system work, right? So fault stability analysis is one of the approach we are taking by knowing all the geomechanical parameters in order to design the well that how far you can be to really keep the integrity, right? And reduce the micro earthquake seismicity. So there are different geomechanical modeling and techniques that we can use in order to understand that how you can better optimize your placement when you have some faults or big fracture system in the field.
Okay, thank you. Okay, now a question from the room. Okay, guys, any questions from the room? Okay, so I'm going to, okay, I have a last one. This is for, this is Nurlan. Okay, is Baker Hughes developing or running geothermal projects to its own needs, or are these integrated services with that Baker Hughes are able to offer to customers?
So we have a different type of projects. Some of the projects are specifically on the one phase of the project, and we also can provide and working on the integrated projects, right? It depends on the customer needs. It depends on the situation. We both going to like a discrete service if the customer only wants, for example, drilling services or drill bits, or they want the full integrated. So we have both end members of the projects in our pipeline.
Okay. Okay. Another question is, can the fracture scale up over time and make the life of the project shorter?
Fracture, yes. So that's a very good question. So I mentioned about this THMC, thermal, hydraulic, mechanical, and chemical changes that we have in the geothermal life cycle. So rule of thumb is that pressure has the immediate impact on your fracture system. Temperature, because the thermal cycling has the medium impact, and then the chemical, also the chemical dissolution and participation because of the temperature and pressure changes also impact on the fracture system. So this is a very complex situation, and we need to look at it at different time of the cycle to understand that how these factors can change the characteristics of the fracture system.
Okay, excellent. No, thank you so much, and thank you for to the audience for those excellent questions. Okay, no, definitely was a very productive session. Thank you, Ghazal, for your time and making us an space in your agenda. So thanks so much.
So I just want to tell all the students the future is bright. You are the new energy of the energy transition and where we are going. So keep going. And I was sitting there a few years ago, and I wish you all best of luck, and thanks for having me.
Okay, thank you so much. Okay, thank you so much for to the audience. Okay, bye bye, and see you next week in another Tech Talk. Okay, thank you so much.
Thank you, Cesar. Bye bye.
Bye bye.